The next concept we're going to discuss is the concept of voltage. And the idea of this is that the number of positive and negative ions on the two sides of the plasma membranes is unequal. The inside is technically more negative, thus there is a potential for ions, positively charged ions, to flow to the other side. In other words, the membrane potential is held negative. Without even using ATP, we can drive substantial changes because of the potential energy being able to be directed from one side to another. We'll also say that this potential is constant even without a special event, and thus the resting membrane potential of a neuron is held negative. So let's talk about what we're looking at in this picture here. This is what we call a voltmeter, and you'll notice that it's reading at minus 70 millivolts. Well, outside of the cell is a ground electrode that is basically reading 0. It's reading the neutral, whatever fluid, so that you can see that there's a difference from the outside of the cell to the inside of the cell. Here we see a microelectrode that has punctured the cell and therefore is reading what is going on inside of the cell. It's basically punctured right through the plasma membrane. So this is some part of the axon that we're just looking at here. And what we'll notice is that the inside of the cell does read as more negative than the outside of the cell, and that is because along the plasma membrane there are negative charges lined up that oppose and are attracted to the positive charges lined up on the outside of the cell. And just so you know, if we go back to this picture here, we'll be able to see why and exactly what these things are. What tends to happen is that these negatively charged proteins tend to line up on the inside of the cell, and these positively charged sodium ions tend to line up on the outside of the cell. So it leaves you, So it leaves you with this idea that positive attracted to negative across the membrane makes it seem as though the inside of the cell is actually negative. P.S. It's actually not true. It's completely neutral. I mean, everything's neutral. Everything balances out. But this tendency for these things to be attracted to each other across the membrane leaves the membrane with a sensation of having this polarity, this difference from one side to the other. And so, when we attach a voltmeter to the inside of a cell, it tends to read at minus 70 millivolts. That's not an extraordinarily strong. It's not even approaching one entire volt. It's not even close. However, it's just enough of a difference to drive basically everything that happens inside of the nervous system. This tiny little difference from the outside to the in, which isn't even very stable, it's just things attracted across the membrane to each other, allows us to have an established, as I said, an established resting membrane potential that is held negative. And therefore there's the potential. We already know that there's the potential for those sodium ions to flow into the cell. But now that we know that they're basically lined up along the outside of the cell, kind of chomping at the bit to get in, that means that any time they have the opportunity to get into the cell, it's going to be a fast and dramatic situation. All right, so I would, this is the generating a resting membrane potential. This depends on the differences in potassium and sodium ions that are concentrated inside and outside of cells, and also on the differences in permeability of the plasma membrane to these ions. So we're showing different situations that can happen. This kind of gives a summary of things that we're going to be looking at in the future. But let's take a look at just this very top structure here. This is called the sodium-potassium pump. And the sodium-potassium pump actually requires a molecule of ATP to do its work, which is actually not shown in this picture, but take it on faith that anytime you have a pump, you can be sure that it requires ATP to do its work. It's pushing things against their concentration gradient. To wit, what it's going to be doing is it's going to be taking 3 molecules of sodium from inside of the cell and pushing them out. Remember that outside of the cell you have much more sodium than in. So sodium doesn't want to leave the cell. It wants to actually stay in there. And potassium, remember, is in high concentration inside of the cell. And so you're taking potassium from outside of the cell and pushing it in. Okay, so the sodium-potassium pump, although I don't talk about it much more, you should understand that this energy-driven structure, this energy-driven pump that requires a molecule of ATP to do its job and drives ions against their concentration gradients, is the thing that is actually responsible for generating the action potential, the resting membrane potential.